Hello and welcome. I am Pradeep and I am very excited to bring to you this video on network theory. In this video, I will specifically talk about the representation and the mathematical structure behind the networks. When we hear the term network, all sorts of things come into our mind, such as social network where people interact with each other, computer network connecting different computers and information worldwide, or the transportation network of road, railways, and flights connecting different cities of the world. Networks are everywhere and they are present at all scales, ranging from molecules inside a cell to the neuronal network in our brains to human societies and even at the cosmic scale with the network of galaxies. Sometimes we use this network structure even without realizing it. But before we start, I want you to forget everything what you think you know about network, and we will start from the very basic, which is the abstract mathematical language of network called graph theory. Graph theory started in 1736 with the famous paper on 7 bridges of Königsberg by Leonhard Euler. But most of the volume of work in this field is only a few decades old. Many important algorithms such as clustering or path optimization are based on graph theory. Many important tasks in computer science such as job scheduling or research allocation are based on graph theory. Mathematically, a network is represented as a graph. A graph, on the other hand, is a very simple object consisting of only two parts, what we call as vertices and edges. In network terminology, vertices are also known as nodes. The nodes are the entities that we can assign some values, such as individuals in a social network, cities in a transportation network, or a computer in a computer network. Similarly, a node can be anything. It can be a molecule, a company, station, country, planet, or an organism. Node can have static properties that one can quantify. For example, we can quantify the wealth of an individual, or the weight of a molecule, or the population of a country. Edges, on the other hand, defines the relation between the two nodes. The edge between two nodes can be physical, just as the roads between the two cities or the cables connecting two computers in a computer network. An edge can also be non-physical, such as social ties or friendship in a social network. In network language, edges are also known as link, ties, or relations. The set of nodes together with the set of links is called a network or a graph. A simple graph is represented by only these two objects, but there are other forms of graphs which needs additional information. Currently, we will focus only on the simple graphs. Mathematically, an ordered pair of set of nodes and the set of edges is called a graph. For example, consider a set of 5 nodes named from A to E is called the node set, and we can define a set of relation between these 5 nodes called the S sets, defining the links. There are 5 links connecting the given nodes in the graph. The full graph is just the collection of the two, that is the set of nodes and the set of edges. The edges are represented by the pair AB, where the pair implying a connection from A to B, where A is the source node and B is the target node. Now the connection between the two nodes sometimes are mutual and does not have a direction. For example, consider the case of a collaboration network representing the research collaboration between two individuals. In this case, if A is a collaborator of B, this also implies that B is a collaborator of A. A network formed of such connection is called an undirected network, implying that the link does not have a direction. In other words, we can say that the links are bidirectional. There is another possibility that the links can have a direction. Such a case is the trade network between countries in which one country is an importer whereas the other country is an exporter. There is always a directional link from the exporter to the importer, implying which is importer and which is exporter. Such a network is called a directed network, indicating a directionality to the links. There is another characterization of the network based on the links, which depends on the strength of the relation between the two nodes. Consider a directed network of 5 nodes and some relation between them. In this case, all the links have the same weightage and we cannot distinguish between different links. But suppose we add some weights to the links. A simple example is to take the network of the research collaboration that we discussed before. We put the strength of the link as the number of projects in which the two individuals collaborated on. For example, the individual A collaborated with individual B on 10 projects. Therefore, the strength of the link between A and B is 10. The weights in the network can be positive, negative, or fractional, which depends on the system under the study. The network with weights on the links is called a weighted network. Since the original network was undirected, where links does not have any direction, therefore the network with weights is called as undirected weighted network. The edges in an unweighted network contains two elements, the source node and the target node, whereas in the weighted network the edges has three elements, the source node, the target node and the strength of the link. Similarly, we can define the weights for a directed network. An example will be the amount of goods in a trade network can be traded as the weight to the link, or the price of the trade can be treated as the weight to the link. A network can be represented in a multiple ways, but there are two most commonly used representation. The first representation is the edgeless representation, where a network is represented by the list of the links it contains. For example, for the given directed network, there are 4 edges and therefore the edge list has 4 elements. The other widely used representation is the matrix representation. In this representation, a link is represented as a matrix element. The rows of the matrix represents the source node and the column represents the target node. As we see, the rows represents the outgoing connection. For example, node A has one outgoing connection to C. Therefore, the element of row A and column C is 1. Whereas B does not has any outgoing connection. Therefore, it has all zeros in the corresponding row. But the two incoming connection from node C and D. Therefore, there are two non-zero entries in the corresponding elements in the column B. This matrix is called the adjacency matrix. But there are other forms of matrix representation for a network, such as the incidence matrix, Laplacian matrix, the normalized Laplacian matrix, and so on. But we will only focus on the adjacency matrix. In the adjacency matrix representation, a non-zero matrix element IJ represents a link from node I to node J. Usually, adjacency matrix is a binary matrix consisting of only zeros and ones, representing the presence and the absence of a link between two nodes. But in case of a weighted network, the elements are no longer binary and can have values where the values represent the strength of the connection. Both of these representation has some advantages and disadvantages. The edge list format is very easy to understand and one can include any information about an edge such as weights or labels, but it comes with a serious drawback that in order to search a single edge, one has to go through the entire list every time. In comparison, matrix representation is very simple and easy to manipulate edges of a node by only looking into the corresponding rows and the columns. But it also suffers a major issue, that is, a large amount of space is needed to store a matrix. Even when the matrix has only a few links, it takes a lot of memory. The second drawback is with the manipulation of nodes. Each time we add or delete a node, we have to store the matrix again. Now let us summarize what we have learned so far. A network is represented as a graph. There are two representations of a network, the edge list representation and the matrix representation. In edge list representation, a graph is represented as the list of edges where elements of the edge list is an ordered pair representing the connection from the source node to the target node. In the matrix representation, the links are represented as the matrix elements with the source as rows and the target nodes as columns. In the matrix representation, an element ij of the matrix is non-zero if there is a link from node I to the node j in the network. Based on the directionality of the link, we can classify a network as undirected and the directed network. An undirected network, the links are bidirectional and hence we cannot distinguish between the source and the target. This gives a symmetric matrix representation of the matrix of the network. When the links is an undirected network has strength, it is called as weighted undirected network, which can be represented in form of a symmetric matrix called weighted adjacency matrix or the weight matrix. In the weight matrix, the element represents the weight or the strength of the connections. When the link in the network has direction, it is called a directed network represented by a non-symmetric adjacency matrix. With weights, the network becomes the weighted directed network and the corresponding matrix becomes the weighted adjacency matrix.